Sponsored by the Grand Valley State University College of Engineering's Computer Engineering Department, the CE MicroDisplay project was tasked with creating an artistic yet functional model of a microprocessor core.
The core was based off the Harvard architecture, which utilizes two separate lines, one for data and one for instruction memory. The Harvard architecture was chosen for this project for its modularity in creating different sizes for data and instruction memory. Additionally, its different buses allow for faster speeds on the data lines.
The other design constraints for the system required us to use addressable LEDs throughout the system, conform to ADA guidelines regarding hanging objects from a wall, be powered by 120-volt wall outlet, utilized a wired and or wireless operator interface to configure the system, all while having an overall form factor of 4 foot by 4 foot.
One big aspect of this project was our collaboration with the GVSU Department of Media and Visual Arts. With us, they were tasked with designing the art for this system, which is going to be mounted on the front plate as well as the front cover. The space in between these two layers would allow for some depth and parallax when viewing these from different angles.
One big question at the inception of this project was how to artistically represent the inner workings of a 4-bit microprocessor. At the start of this project, our sponsor had requested that both our artistic design as well as general system design did not obviously give away what our system was trying to represent. By doing this, we not only start conversations, but we also spark curiosity in prospective students as well as anyone who may view the system. After initial meetings with the Grand Valley State University Department of Media and Visual Arts and sketching, we had decided to choose a cyberpunk cityscape as our design language. By choosing this, we not only pay homage to the technical aspects of this project, but we also utilize it to gain the attention of anyone who may pass by to start conversations on what this system is trying to represent. Our final solution utilizes an ESP32 that can be controlled and configured both over UART as well as wireless Bluetooth to configure custom-made LED displays and LED strips made from the WS2813B LED variant. The overall system was designed in a modular fashion and includes several features such as backup data lines on the LED control circuitry, cooling circuitry including a thermistor and several fan headers, as well as the inclusion of the readily available and standardized IEC C14 plug with an integral power switch which matches with an IEC C13 cable. This is all encased in a protective frame with artwork on the front designed and provided by the GVSU Department for Visual and Media Arts. This system protrudes from the wall at 3 1/4 inch, meeting strict ADA guidelines dictating a maximum depth of 4 inches. The default program the system runs is an add command. The program immediately starts when the system is turned on and will continue to run indefinitely until power is switched off to the system or it is reconfigured by an operator over Bluetooth or UART.
Which consisted of 7 layers: the front cover, a spacer plate, the front panel, another spacer, the back plate, the frame itself, and then the back cover.
When it came to manufacturing our enclosure, we had 7 layers that we had to put together and assemble. The CNC machine at GVSU was used to cut out our backplate, where brackets, screws, and nuts were used to adhere them together. And the laser cutter was used to cut out our front plate, which was cut up into 9 pieces, and acrylic bonding cement was used to adhere all of those together. Whereas nails and screws were used to put together our frame, and acrylic bonding cement was also used for our spacers. One of our main design constraints for our enclosure system was ADA guidelines, which stated no objects hanging at higher than 27 inches above the wall must protrude no more than 4 inches from the wall in order to meet accessibility needs of people who may end up using the building. While we designed the system, we ensured that we minimized this height by limiting the depth in order to be large enough to accommodate for airflow to the power supply and system cooling, but also small enough to maintain a total depth of 3 1/4 inches, being smaller than the ADA guidelines of 4 inches.
Electrically, design was split into 4 systems: the power PCB, our display boards, the system wiring, as well as a power supply for the overall unit. For this project, we decided we need to make our own custom display LEDs, as the ones on the market, such as 7 segments, did not meet our needs.
For this project, we designed a total of 3 display boards. A 2x2 display board meant to represent single-bit values, either on or off, as well as a 4-digit and 8-digit display board meant to represent numerical binary 1 or 0 values.
In addition to the 3 custom LED displays, we designed a power PCB board. The main goal of this power PCB board was to serve as a mount for the ESP32, contain power injection points for the LEDs, contain in-out ports to control these LEDs, and in-out ports to control the cooling fan. The entire system was powered by an LRS 600 5-volt power supply that was connected to wall power using an IEC C13C14 receptacle and cable kit. An additional cover was 3D printed on top of the power supply output ports in order to protect operators from potential shocks. The output was connected to the power supply board, which connected power to the rest of the system.
When it comes to manufacturing, we had a large amount of boards to populate, utilizing very small LEDs with a footprint about 3.5 millimeters by 3.5 millimeters. Assembling these by hand would have been impractical and time-consuming. Fortunately, Grand Valley State University has a pick-and-place machine that we utilized to our advantage. A large number of PCBs throughout the system, one of the big considerations was how to wire the system, both for power and data. We utilized several different types of wire harnesses as well as connectors to connect power through several circuits as well as data through several circuits to help widen the load and data burden onto our power supply as well as microcontroller.
This was due to the LEDs that we used in the system. Per the datasheet recommendation, no more than 300 LEDs should be connected in series before a power injection point. In addition to this, no more than 1,300 LEDs should be controlled by a single I/O port to maintain signal integrity. As a result, our system of over 2,000 LEDs contained 10 power injection points and 3 I/O lines to ensure that we were well below the recommended maximum values.
With a large amount of LEDs and wiring within this system, a significant amount of the build time was spent performing cable management as well as verifying the connection to these LED strips. One key hurdle we faced in this build process was the tight bend radiuses needed to install the backplate, which had the LED strips mounted into this frame. To address this, we added heat shrink, which served as stress relief, ensuring that all of our solder connections remain stable once installed.
Is broken down into 3 major categories. The LEDs that control the animation and display information to an observer, the communication protocols that allow an operator to change the program that is being ran on the microdisplay, and the third one is a temperature control unit.
The temperature control system is comprised of a single thermistor, an analog to digital converter on the ESP32, which controls a single fan.
The system is configurable through 2 different communication protocols, a wired communication using UART and a wireless communication protocol using Bluetooth. You can configure the system to perform different operations such as a logical AND or a logical OR operation. In order to be able to control the model, we ended up creating a Python tool that could utilize actual C code that we would later use on the model. This allows us to develop the code without the need of physical hardware. Once we ported it over to the system, we used ESP32's inbuilt LED strip library. This allows us complete control over any LED in a strip, allows us to set it to whatever RGB color we want it to. This animation starts by loading the program with default values and then begins to run. The first thing the program does is clear the value of both the A and B registers. This ensures the value of the registers are not going to be modified once we begin the actual program. Afterwards, the program loads each of the registers with a specific value. The first register, the A register, is loaded with the first value in the data memory registry. This is the value of 15. Afterwards, it begins to do the same thing with the B register. The B register gets loaded with the second value held in the data memory. This value is 2. After the values have been wrote to both registers, the program then decides to perform an add operation on both values. The 2 values are added together, the ALU flags are updated, and then the exported result is held in the A register. Afterwards, the A register's value is then outputted to the out port in order for an observer to be able to view. The program then runs a jump command, which allows the add and output instructions to be looped for an indefinite amount of time.
With the system now assembled and over the last 6 months, the CE MicroDisplay project team, its sponsor and advisors are all excited to see this product be used as a recruitment tool and to spark curiosity into the next generation of West Michigan engineers.